All right, welcome back, everybody. So we've got just a couple more slides to do out of. Let me get the
Substitution rule.
out of the substitution rule section. Um, so what we're going to be looking at today, yesterday we focused on indefinite integrals. Today, what we're going to talk about is definite integrals. Okay, so nothing new today. Same process as we had yesterday, but now in the end, instead of just writing the plus c, we'll have boundaries where we can actually plug in and evaluate. All right?
How are you going to substitute a definite integral?
You work it the exact same way.
Okay.
Yeah. So let's talk about the process of the substitution rule for an indefinite integral. Remember, what you have to do is define your u. Define your u. And remember, you look at the innermost function. Like if you're looking at a composition of things, like here, that x to the fourth plus 2 is our u. We differentiate both sides. So du was 4x to the third dx. And then we look for what we had here, that x to the third dx. And we say, okay, well, I need to get that 4 over to the other side. You divide it over to the other side. And so 1/4 du was x to the third dx. Substituting cosine u. Then we do the integral. We perform the antiderivative, 1/4 sine u plus c, and then in the end, take that x to the fourth plus 2 and plug it back in. So that's the process, right? That remains the same. What we're going to do here at the end is then say, well, once you plug it back in, all you have to do is put that vertical line top minus bottom, enter it in, done. Okay? And that's really the new part for today. Okay, so definite integrals. Now, here is a kind of fancy rule that we can work with. So there is something that we can do when we do use substitution. When evaluating a definite integral by substitution, two methods are possible. We could really do two things. And it's really 6 of one, half dozen of the other. It really is, you're performing the exact same definite integral. One method is to evaluate the indefinite integral first, and then use the fundamental theorem, FTC2, right? The exact same thing as you probably would think that you should do, where we get to the end, instead of writing the plus c, we draw that vertical line, top minus bottom. Done, easy peasy. No more work needed. That's totally fine. But there is another way. There is another way. When we do use substitution, what we can actually do is change the definite integral. We can actually change the definite integral. Watch what I can do here. You know how we had b minus a? Instead of reverting back to that old b minus a, what we can do is actually take whatever we decide u to be. We can run those values through u to change our endpoints. Because, think about it yesterday. Think about yesterday. Every time we plugged the values back in, weren't we making this more complicated? Right? So if there was some way to evaluate it only with u, our life would be a little bit easier. Not like drastically easier, but just a little bit easier, right? Like if I jump back to the problem before, here, that's not a good example. Like this. In the end, I was left with this. And we found the integral to be this. We could plug x back in. Totally acceptable. And use our definite integrals. But what we could also do is use this simplified version of the u equation. Now, in doing so, here's what we have to do. We have to take off the a and the b. And what do we do to it? We make it g of a and g of b. And what is that? That is, you take your u and you run those values through u to create a new g of b and g of a. Here's what I mean. Let me show you what I mean. Okay? So definite integral of the square root of 2x plus 1 dx. Definite integral of the square root of 2x plus 1 dx of 0 to 4. Okay, so what do you think my u is going to be in this case? 2x plus 1? Pretty logical guess here. U is 2x plus 1. So now I chose my u. I'm going to differentiate now. So du, come on, du is 2 dx, right? Because the derivative of 2x is just 2, and the 1 will go away, and don't forget we have to tack on the dx. Okay, now, is there anything, like think about it this, I have square root of u now, and then dx. Is there anything with the dx? No. So that means I need to get this 1/2 over to the other side. So dx is equal to 1/2 du. Now, you know what I can do for my top and bottom numbers? Instead of using 0 to 4, what I can do is run 0 and 4 through u. Here's what I mean. What is 0 times 2 plus 1? 1.
Oh, 0.
0.
I said 4. I was so confused.
You're good. What is 2 times 4 plus 1?
9.
Solid. What I can do is just change those numbers. And all I did was just evaluate u of 0 and u of 4. Right? I just ran it through u. Because now what I can do, I'm just going to manipulate it a little bit more. I'm going to keep it going. 1 to 9 of 1/2 u to the 1/2 du, right? Because I like to write it as exponents rather than a square root. I brought that 1/2 out in front. And now I'm going to evaluate this integral. Okay, so that's 1/2 u to the 1.5 over 1.5 from 9 to 1. Pretty simple, right? So this is 1/2 times 9 to the 1.5 over 1.5 minus 1/2 of 1 to the 1.5 over 1.5. F of b minus f of a. Okay, so I have 0.5 times 9 to the 1.5 divided by 1.5. That gets me 9. Okay, cool. And then I have 0.5 times 1 to the 1.5. That's just going to be 0.5. Divided by 1.5, which is 2/3. Or 1/3, excuse me. 0.3. So that's 8.6 repeating, right? We're 26/3. What a nerd. 26/3. But again, that's 8.6 repeating. So what did I do here? Let's kind of take that back a step and think about the process. You choose your u value, you choose your u expression, I guess. Differentiate. You got to do this whole part where you got to look at the equation and see how I can match it up, how it goes in. Got to get the 1/2 over to the other side, input the 1/2 du, and at that point, what I can do is change my definite integral. See, 4 turned into 9, 0 turned into 1. And how did we do that? We ran it through u. Okay, we did this through u. Then I performed the antiderivative. I performed the integral like I always would. The other option of doing this problem would have been to do this. At this point, go back and say, okay, 1/2 2x plus 1 to the 1/2 du, or sorry, I'm sorry. Sorry. At this point, go back and say 1/2 right here, excuse me, 1/2 times 2x plus 1 to the 1.5 over 1.5 and do this from, where did we start? 0 to 4. See, that is equivalent to that. And that just complicates, like the green just complicates our life a little bit more because there's another additional expression within there. So I am always going to do this, where we change our parameters of a to b. okay, where I can change those, run it through u, so that our life is just a little bit easier in the long run. Okay. Let's try another one. You're going to go from 1 to 2 of dx over 3 minus 5x squared. Okay, what do you think our u is? 3 minus 5x. Okay, so du is negative 5 dx. Okay, just manipulating this a little bit. Isn't this still 1 to 2 of 3 minus 5x to the negative 2 dx? You follow what I did there? I pulled out the dx to the right side. And instead of having it in the denominator, I just made it a power of negative 2. Just to kind of simplify it a little bit. All right, I don't see this negative 5 sitting anywhere here, so I got to get it over to the other side. Negative 1/5 du is dx. So here's what I can say. I'm going to change colors now because I'm now inputting u. This is going to be u to the negative 2 times negative 1/5 du. Notice how I left open my integral. I haven't written my a and b. Because now what I do is I run 1 and 2 through 3 minus 5x. Okay, I've got to run 1 and 2 through 3 minus 5x. So 3 minus 10 is negative 8. 3 minus 5 is negative 2. Wait a second. No. Just our u. Just going through u. What did I do? Oh, yeah. 3 minus 10 is negative 7. Whoa. Weebo. Yikes. I was like, why do I have a 7? Okay. Again, all I did was run it through u. You're not running it through anything of the original function. You kind of have to ignore that for a second. All you're doing is running it through u. 2 turned into the negative 7. 3 minus 10 is negative 7, not negative 8. And then the 1 turned into the negative 2. 3 minus 5 is negative 2. Okay, so now we just have to evaluate that integral, which is, okay, so this is going to be a u to the negative 1 over negative 2. Oh, I forgot my negative 1/5. And I'll put that up in the top. Negative 1/5 u to the negative 1 over negative 2. Oh, sorry, negative 1. Whoa, I'm screwing up this problem. Negative 1/5 u to the negative 1 over negative 1. And I would say, if this was an indefinite integral plus c, but this is not, this is a definite, negative 7 to negative 2. Okay, so that's going to be equivalent to negative 1/5 times negative 7 to the negative 1 power. Actually, can't I just divide by the negative 1 to make this positive? I'm going to do that first before I move on to the next step. 1/5 u to the negative 1. Negative 7 to negative 2. Because the divide by negative 1, all that's going to do is just cancel out that negative in front. So that's going to be 1/5 negative 7 to the negative first minus 1/5 negative 2 to the negative first. Okay, let's evaluate. 1/5 times negative 7 to the negative first power. So we have that decimal. negative 0.029 minus 1/5 times negative 2 to the negative first power, which is negative 0.1. So we have negative 0.029 minus a negative 0.1. 0.071. Questions about that? Got one more of those to do. Let's take a look at the next one. What do you think your u is going to be in this case? What do you think? ln of x. Yeah. I'm going to pick my u to be ln of x. U is going to be ln of x. You kind of have to use some intuition here, because thinking about it this way, like if I were to rewrite this, couldn't I say this? From 1 to e of ln of x times, don't use parentheses, times 1 over x dx. What is the derivative of ln of x? 1 over x, right? So du is actually going to be 1 over x dx. Hey, look at that. How fancy. It's nice when things work out nicely like that. So this is actually going to be the integral, I'm going to leave it open for a second, of ln, so it's just u du. Look at that. That's really nice. U du. Because ln of x was u. And du is 1 over x dx. Now, the tricky part here is figuring out, I guess it's not so tricky, remembering to change up our a and b. Okay, so top is e. What is ln of e? If we don't remember, ln of e, it's just 1, right? Because it'd be log base e of e. Those would cancel, just leaving a 1. So ln of e is 1 up top now. And then ln of 1. And what is ln of 1? 0. Okay, let's antiderivative, which is u bumped up to second over 2 from 0 to 1. Man, that's nice and simple. So this is 1 squared over 2 minus 0 squared over 2. Well, that's just 1/2 minus 0, so 1/2. That's a pretty simple one.
No. Yeah.
Talking about lucky numbers?
Yeah. Mr. Albert, what's your lucky number?
13.
13?
Yes.
That's an unlucky number.
No. You want to hear why?
Why?
So my first name is Brant.
Yeah.
It starts with a B. It's a B.
Okay, I like it. I like it.
So 13. All right. Okay, last example that we have, last new piece here, really is not very new. Okay? It's actually not new. It's actually something that we've talked about before, you've done examples of, but we haven't really discussed it and haven't really created a rule for it. It's when things are symmetrical. Okay? It's when things are symmetrical. Like think about, for example, a couple different types of symmetrical equations. Like x squared. Think about x squared. Just the parent function x squared. This has even symmetry, right? Okay, if I take the integral that's equal in terms of value, in terms of absolute value, if I took the integral of two places that are equivalent distance-wise to the axis, say I went from over here at negative a to positive a, what's going to happen to my area? Well, I'm going to have this area, and if this is symmetrical, aren't I going to get the same exact area over here? So it's essentially 2 times the area from 0 to a, right? Which helps us a little bit, because what's nice about having a 0 on the end down there? Usually it's going to say minus 0 on the end, right? It kind of helps us a little bit because it's going to have a minus 0 on the end. We saw this on our last test when we had to do something where, it was bounded by this, right? And I said, people are always going to think this is going to cancel out. It's not going to cancel out because, again, this is even symmetry, right? That area is going to be equivalent to that area. So it's not going to cancel out. It's actually going to double. Now, if I turn that around, if I think about something that has an odd symmetry, something that is going to have an odd symmetry, our most basic odd symmetry, or one of our most basic odd symmetries, is the cubic, right? If I do the same thing where I take negative a and positive a, negative a and positive a, and I find those areas, what's going to happen now? Well, I'm going to have this area here and this area here. Aren't those going to be equivalent areas? Except one's negative and one's positive. So what's going to happen to the area every single time I make that the same value? It's going to be 0 every time. Okay? So if you can tell something has an even symmetry, and you're looking at it from negative a to positive a, it's going to double. If you can tell that something has an odd symmetry, you're looking at it from negative a to positive a, you know it's going to cancel out. Okay? Let me show you a couple examples here. Actually, let's just look at this one example. Since f of x is equal to x to the 6th plus 1, since that is an even symmetry, how do you know it has an even symmetry? If I plug in negative x, guess what happens? It turns back into f of x, right? Negative x to the 6th power turns into positive x to the 6th power plus 1. So it's even. Since I know that it's even, no matter what I choose, as long as I choose the same value left to right, negative 2 to positive 2, negative 2 to positive 3, it's going to double in size. So, for example here, negative 2 to positive 2 of x to the 6th plus 1 dx is going to be the same as 2 times 0 to 2 of x to the 6th plus 1 dx. How does that help us? Well, again, if we choose the 0 one, that's going to turn our whole right side into 0. So it's just going to be like 2 times 0 to 2, right? 2 times 0 to 2. That's, again, if something has even symmetry. If something has odd symmetry, now they give a really obscure example. Like, look at the example that they give. It's like, what the heck is that? Let me show you a better example of something that has an odd symmetry. Okay. Yeah. What's going to happen to my areas there? They're going to cancel. I think we talked about this a little bit before. The sine and cosine graphs, if you put them in the same, if you get it just so, 0 to 2 pi, intervals of 2 pi there, you're going to get them to cancel out again. Okay. All right. So that's all I got for the notes for today. I want to give you about a half period to work. Let me put the assignment. Let me stop recording.